Hello everyone, and thank you so much for tuning in to the second part of my two-part video series on finding the limiting reactant of a chemical reaction. If you're interested in watching part one, or if you're interested in watching any of my stoichiometry content, there are links to it down there in the description. So without further ado, let's go ahead and get started with the first problem. So this problem shown on the board here says we have this balanced chemical equation right here where we've got iron 3 oxide, or ferric oxide as you may know it, reacting with 3 moles of hydrogen gas to produce 2 moles of water and 1 mole of aqueous sodium sulfate. And we're also given some more information right here. So we're given that we have 33.12 grams of iron 3 oxide, and this hydrogen, since it's a gas, the problem tells us that we have 3 atmospheres of pressure. The pressure is 3.0 atmospheres with a volume of 4.5 liters and a temperature of 100 degrees Celsius. So the idea here is that we're going to use all of this given information to convert each of these two reactants to what unit do you think we're going to convert to? If you guessed moles, you would be correct. So we want to convert both the ferric oxide and the hydrogen to moles. And this is going to be the case with any stoichiometry or limiting reactant problem. Is moles is the goal, right? The goal is to get to the mole. And the reason why is because the mole is the unit with which this balanced chemical equation is compatible, right? This chemical equation says 1 mole of iron 3 oxide reacts with 3 moles of hydrogen to produce 2 moles of water and 1 mole of sodium sulfate. So in order to use this balanced chemical equation as the sort of recipe to figure out which one of these two is the limiting reactant, we have to convert both of our reactants to moles. Now, some problems are going to be really easy where you're going to be given moles from the beginning. Other times you're going to convert from mass to moles. In this occasion, we're going to convert from mass to moles with one reactant, and then we're going to use the ideal gas law equation. If you studied gases before, I'm sure you know that one by heart, or at least you should, to convert to how many moles of hydrogen we have. So I think the easier one is converting from mass to moles, which is what we're going to have to do in the case of this iron 3 oxide over here. So if we go ahead and set up our given information here and then use a conversion factor to convert to moles, right? So we're given that we have 33.12 grams of this iron Fe2O3, right? 33.12 grams of iron 3 oxide. So what I'm going to do is I'm going to set up this conversion factor here. So I'm going to multiply by something, I'm going to divide by something. The unit that I'm dividing by is going to be the grams. That's what I'm trying to get rid of. So I'm going to put grams of iron 3 oxide on the bottom, and I'm going to put moles of iron 3 oxide on the top, right? So the conversion factor at the bottom is always going to be the unit that you're trying to convert away from. At the top is the unit that you desire. In this case, that's moles, right? So the question then becomes, what numbers belong in the numerator and denominator of this conversion factor? And it's going to be 1 mole of iron 3 oxide, and so we need to figure out how many grams of iron 3 oxide are in 1 mole of iron 3 oxide. And the way that you do that is by consulting your periodic table, and you're going to add together the masses, the atomic masses, of all of the atoms in the periodic table. So with Fe2O3, we're going to have 2 iron atoms and 3 oxygen atoms. So if we take the mass of 2 iron atoms and we add that to the mass of 3 oxygen atoms, then that'll give us the mass of the ferric oxide. So I'll go ahead and do that calculation down here real quick. I want to make sure I get all the steps involved so nobody can be confused as to how I got from one part of the problem to another. So if I have 2, so if we're talking about the iron atoms in this, right? There are 2 iron atoms. So if I have 2 and I multiply that by the molar mass or the atomic mass of iron, if we look that up according to our periodic table, that's going to be 55.845 grams. So that's how many grams are in 1 iron atom, and we're multiplying it by 2 since we have 2 iron atoms in our formula here. And I'm going to add to that 3 times the molecular weight or the atomic weight of oxygen, which is 15.999 grams. Sometimes you'll see 16.00. It just depends on how many decimal places your periodic table wants to go out to. So this is how we arrive at the formula for iron 3 oxide. And at this point, I would invite you to pause the video and perform this calculation for yourself just to make sure that we're all on the same page. Okay, I think enough time has passed. And the number that we get is 159.687. 159.687 grams of ferric oxide, or in 1 mole of ferric oxide, right? So if we perform this calculation, basically it's going to be 33.12 times 1 divided by 159.687. The grams of ferric oxide are going to cancel, and we're going to be left with moles of ferric oxide, which is good because that's what we want, right? And according to my little cheat sheet that I've already completed ahead of time, that's going to be 0.2074 moles of iron 3 oxide. So we know how many moles of iron 3 oxide we have. Now we need to figure out how many moles of hydrogen that we have. Now in this example with the iron 3 oxide, it was fairly easy. We just had to use a simple molar mass conversion, just use the molar mass to convert from mass to the amount in moles. But this one is a little bit different, right? We're not given a mass. Instead, we're given a pressure, a volume, and a temperature. And somehow we have to turn that into moles. So as I mentioned previously, the equation that we're going to be using is the ideal gas law equation, which is, of course, PV equals nRT. So P, that's the pressure, V, that's the volume, N, that's the amount in moles, R, that's the ideal gas constant, and T, that's the absolute temperature, right? And so if we just play around with this equation algebraically, let's say we want to isolate moles, right? Because we have pressure, we have volume, we have temperature. R, that's just a constant, so we can just plug that in and refer to it in our chemistry textbook if we don't already have it memorized, which I do because I've done this a bunch of times. But if we just play around with this equation algebraically, we want to isolate N, the amount in moles. That's what we're trying to convert to. So if I divide both sides of this equation by RT, then I'll isolate N. And so rearranging, we get N is equal to PV over RT, right? So really all I have to do to figure out how many moles of hydrogen we have is to take the product of the pressure and the volume and divide that by the product of the gas constant and the temperature. So if I go ahead and do that, I'll have the N, and I'll just put sub H2 here. Moles of hydrogen is going to be equal to, and again, that's the product of the pressure and the volume. In this case, our pressure is 3.0 atmospheres, right? 3.0 atm. The volume, in this case, 4.5 liters, 4.5 liters. So that's our numerator. And our denominator, well, let's try that one again, is going to be the product of the ideal gas constant and the temperature. Now, the ideal gas constant, this is something that you can look up, and in all honesty, it's really something that you should have committed to memory. It will pop up over and over and over again, and that is 0.08206, and that's liters times atmospheres over moles times kelvins. So that whole thing, liters, atmospheres over moles, kelvins, that's the unit of the ideal gas constant, right? So that's R. Last thing we need to plug in here is the T. That's the temperature. Now, be careful with this because the problem says that we're given a temperature of 100 degrees Celsius. But notice that the temperature, or the unit rather, in the ideal gas constant is Kelvin. It's not degrees Celsius. So in order to use this temperature value in our ideal gas law equation, we need to convert it to a unit that's compatible with this equation, right? And that unit is Kelvin. So that's just another basic conversion that you should probably have committed to memory, is that when you have a temperature in degrees Celsius and you wanted to convert that to Kelvin, all you have to do is add 273.15. And so if you have 273.15 added to 100, that's going to be 373.15 kelvins, right? And so before we start plugging the numbers in, let's just make sure that our units cancel. So we have atmospheres up here, that cancels with atmospheres down there. Liters up here cancels with liters down there. Kelvins over here cancels with kelvins over here, and we're left with nothing but moles, which is good because, again, that's what we want, right? All right, so hopefully we can pause the video if you want to, but we're going to go ahead and plug these values into the calculator. 3 times the product of 3 and 4.5 divided by the product of 0.08206 and 373.15. And the number that I got is going to be 0.44 moles of hydrogen, right? So at this point, we know how many moles of each reactant we have. We know how many moles of ferric oxide we have. We know how many moles of hydrogen we have. And so we are all but ready to figure out which one of these is the limiting reactant. Now, I'm going to need a little bit more space on my whiteboard here, so I'm going to do a little bit of erasing. Oh wait, I should not have erased that. I'll write it again, don't worry. So what was it? We have 0.2074 moles of Fe2O3, right? And then, whoops, looks like I accidentally erased this one too. I'll go ahead and write it in again. We have 0.44 moles of H2. Okay, so now that we have each of our reactants in moles, now what we need to do is figure out how much of one reactant is needed to react completely with the other, and then compare that value to how much of that other reactant that we have, and figure out if we have too much or if we have not enough, right? So that's kind of a long-winded sentence, but I think if you stick around with me, we can sort of elaborate on that, right? So what did I say? I said we need to figure out how much of one reactant that we need to react completely with the other. So let's just say, for instance, that we start out with our 0.2074 moles of Fe2O3, right? So I have this many moles of iron 3 oxide, and I want to know how much hydrogen is required to react completely and consume all of this 0.2074 moles of Fe2O3, right? Well, the way that I would do that is that I would set up what's called a mole-to-mole conversion, in which I convert from moles of this stuff, moles of Fe2O3, and I would convert that to moles of hydrogen, H2, and what's going to populate the numerator and denominator of my conversion factor are the coefficients from my balanced chemical equation. Now, in front of the Fe2O3, there's nothing there, so that's an understood value of 1, right? And then in front of my H2 here, there's a 3, right? So make sure we cancel our units out here. And so we get 0.2074 times 3, and that's equal to 0.6222 moles of H2, right? And again, this value, I'm going to move my board over here. It looks like I'm off the page a little bit. This represents how much we need if we wanted to react with all of our iron 3 oxide, right? Now over here, this value right here that we calculated earlier using the ideal gas law equation, this represents how much we actually have as given by the information in the problem from the beginning, right? So take a look at the numbers, right? Do we have more than enough hydrogen that we need to react with all of our ferric oxide, or do we not have enough hydrogen to react completely with all of our ferric oxide? Well, looks to me like we don't have enough, right? Because it takes 0.6222 moles of hydrogen to react with all of our iron 3 oxide, but we only have 0.44 moles. So therefore, the hydrogen must be our limiting reagent, right? So if we were to run this chemical reaction with the quantities that were included at the beginning of the problem, the hydrogen would run out first, because again, that's what the limiting reactant is. It's the reactant that runs out first. I didn't define that at the beginning of this video, but hopefully, I'm assuming if you're watching this video, you have a good solid understanding of what the definition of limiting reactant is already. So, all right, I hope that problem helps. So I'm going to go ahead and set up the next problem. It's going to require a lot of erasing, so bear with me just a sec. I might do like a little quick time montage here. Hang on. Okay, so I've just set this problem up for you guys, so I'll go ahead and sort of just go through it briefly. So we have this balanced chemical equation over here where we have 2 moles of aqueous sodium hydroxide reacting with 1 mole of aqueous sulfuric acid to produce 2 moles of water and 1 mole of aqueous sodium sulfate, right? And the other information that is given by this problem is that basically we have these 2 aqueous solutions that are mixed together, and the sodium hydroxide, it tells us that we have 27.4 liters of it, and that its concentration is 6.98 molar. And as for the sulfuric acid, we have a volume of 48.2 liters and a concentration of 3.81 molar. So just like the last just like the last problem, the goal is to convert both of these to moles so that we can do that comparison of how much we have versus how much we need of one reactant to react with all of the other, right? But what is different between this and the last reactant is sort of the last problem is the nature of the reactants. In the last reactant, one of the reactants was, I keep mixing up reactant and problem. In the last problem, one of the reactants was a solid and one of the reactants was a gas. And in this case, both of our reactants are aqueous solutions. So depending on the nature of the reactants and the information that's given, that's going to sort of result in different methods of converting to moles, but the end goal is always the same. It's to convert to moles and then do the comparison to find limiting reactant, right? So in this case, we have the volumes and the molarities, hopefully you understand that term, molarity, of these two solutions. Now whenever you see this term, this unit right here, this capital M, that stands for molar, and what that means is that you have a molar concentration, right, which is the 6.98 molar. That is the same thing as saying 6.98 moles per liter, right? Moles over liters. And so if I just substitute that in, moles over liters, then I think it starts to become apparent how we can convert each of these to moles, right? We have moles per liter, we have liters, we need both of them in moles. So this is a sort of a solution stoichiometry problem, right? So if I start, for instance, with our I'll just start with our sodium hydroxide over here, right? If I start with let's say I start with my 27.4 liters of sodium hydroxide, well, I can use that molar concentration that's in moles per liter, I can use that as a conversion factor to convert from volume liters to moles, right? So this concentration of 6.98 moles per liter tells us that there are 6.98 moles of sodium hydroxide. Then I didn't write that very well because I didn't give myself enough room. Let me try that again. 6.98 moles of sodium hydroxide in 1 liter of sodium hydroxide. That's what a 6.98 molar solution means. It's that for every 6.98 moles of sodium hydroxide, we have 1 liter of that. For every 1 liter of that solution, we have 6.98 moles. Okay, you get the idea. Let's proceed. So the units liters are going to cancel, right? Liters of sodium hydroxide cancels out with liters of sodium hydroxide. And as I always would suggest, go ahead and punch that into your calculator, pause the video if you need to, and we end up getting a value of, I can't even read my own handwriting. I think it's 191 moles of sodium hydroxide. Yeah, that's 191 moles of sodium hydroxide. Now, if we do the same thing, the same approach, the same exact approach with the sulfuric acid, well, how much sulfuric acid do we have? We have 48.2 liters of it. So if I start out with my 48.2 liters of H2SO4, I'm going to do the same thing where I use the molarity, the molar concentration, as a conversion factor to convert from liters of H2SO4 to moles of H2SO4, right? And in this case, it says we have a concentration of 3.81 moles per liter, so that means there's 3.81 moles for every 1 liter of the sulfuric acid. So if we go ahead and make sure our units cancel, liters of H2SO4 cancels out with liters of H2SO4. And so it becomes, if we just punch this into a calculator, 48.2 times 3.81, that's going to be a value of 184 moles. And I'll go ahead and sneak in my H2SO4 down there, right? 184 moles of sulfuric acid, and we have 191 moles of sodium hydroxide. So at this point, you might be tempted to say, oh, well, you know, we have less sulfuric acid than we do sodium hydroxide, so that must be the limiting reactant, right? Well, not necessarily, because we have to consider the fact that we have coefficients. We have a balanced chemical equation that tells us how much of each reactant to put into the recipe. So it not only depends on how much we have, but it also depends on how much we need. So the next step, we're going to do the same thing that we did in the last problem, which is to determine how many moles of one reactant are needed to react completely with all of the other, and then compare that value to see how much do we have versus how much we need, and then we make our judgment on that accordingly. So I'm going to go ahead and just erase some of this stuff just to give myself some more room to perform that conversion. Okay, so I've left up my 191 moles of sodium hydroxide and my 184 moles of sulfuric acid. So again, we're going to figure out how much of one reactant we need to react with all of the other. So if, let's say, since this one is on the bottom, I'll start out with my 191 moles of sodium hydroxide. And I'm going to set up my conversion factor, right? I'm going to do a mole to mole conversion. And again, the goal here is to figure out how much of that sulfuric acid do I need to react with all 191 moles of this sodium hydroxide, right? And so we're going to put moles of NaOH on the bottom. And we're going to put moles of H2SO4 on the top, right? Now, and again, what belongs in these spaces here is the coefficients from the balanced chemical equation. So In the case of sodium hydroxide, we have a 2. And in the case of the sulfuric acid, we have an understood coefficient of 1. Canceling the units, moles of sodium hydroxide, moles of sodium hydroxide. It's going to be 191 divided by 2, which is going to be 95.5 moles of H2SO4. Right? So now that we know how much H2SO4 is needed, so this is what we need, right? This is what we need to react with the 191 moles of sodium hydroxide that we have. And over here, as we calculated earlier, this is how much sulfuric acid we have, right? So we have 184 moles of H2SO4. We only need 95.5 moles of it. So we have more than enough, which means that the sodium hydroxide, this stuff, the NaOH, that is our limiting reactant. So, all right, so that was just a couple of examples. I've got some more content planned, so feel free to stay tuned. Thank you very much for watching this video. I would definitely appreciate if you found this video helpful that you would maybe slap a thumbs up on it. It would really go a long way to help me out, so thank you for even considering it. And if you're not already subscribed, I would highly recommend subscribing. That way you can be notified. Click that notification bell so you'll be notified the instant my next educational video is published. So, all right. Thanks you guys. I really appreciate it. Got more content on the way, and talk to you soon.